That's a funky sound.
All right, so in calculus 1, you did something known as implicit differentiation. You had to have actually. Yeah, because the only way to find the integrals of, or not the integrals, the derivatives of logarithmic functions is implicit differentiation. So to like find the integral or the derivative of log base 2 of x, like you have to do implicit differentiation to do it. Until just memorize the rule of it. So implicit differentiation basically allows you to find a derivative of a function that's in terms of x and y. Okay, so if I had an equation, it was like 3y squared equals 4x squared plus 2, for example. We were going to do the ddx of both sides. So this one, I would, finding the derivative, it'd be 6y dy dx, because you have to basically do the chain rule for that extra y. Okay, so because y is not a variable in essence, it's a function. It's a function in terms of x. So same thing with this side, we would divide this side, so or find the derivative of the side, so we get 8x. So the dy dx is 8x plus 6y. Or not plus 6y, sorry. 8x divided by 6. So that's now my derivative of that function. Okay. So if we had like circles and stuff like that, where you have terms where you cannot solve it necessarily just for y, there are functions that cannot be solved for y. We still have to be able to find the derivatives of it. Well, that's great. And this is what differential equations is about. Is we have a derivative of a function, or we have the rates, we have the rate of change and stuff like that, which we would consider the derivative, and we need to find the initial equations for that. So we need to be able to find the initial functions, which is what we do typically with integration. However, not every function or not every equation that we would need to do that to is a function that I can solve for y or f of x. So differential equations allows us to be able to do that with multiple variables. Separatable equations is one of those things. This is the one out of chapter 9. This is the one that I choose to do because I think it's the easiest one for you guys to get, and it connects with the other stuff that we've been doing. So we would want to basically look at this one, and how do we take this one and go backwards to this? Okay, how would I take this and go backwards and find the original equation for this problem? We would have to do the integral of it. Okay? So
multiply both sides by 6y.
We did. We got dy dx equals 8x over 6y.
And I'm going to work backwards from that.
Yes, but to go from here, that's basically what you would do. So when we're looking at a separable equation, if you notice, this looks just like this. It's an equation that I can separate into two specific pieces, one with the y's, one with the x's. Not every function you can do, or not every equation you can do this to. So not every equation will be considered separable. All right, separable one is ones that I can specifically split it up into the x's and the y's, like the example that I have right here. I can take this problem and I can change it by multiplying both sides. So I have 6y dy equals 8x dx. Then I can take the integral of both sides. So what's the integral of 6y?
Y squared
it's 6y to the third over 3, which is second, not 3, which ends up being the 3y squared. I was looking at this, I was writing this and looking at the 3y squared. Plus c equals this side is 8x squared over squared, which is 4x squared plus c. You do not have to put the c's on both sides.
Can I?
So this and this. No.
Okay.
You can. However, they don't cancel each other out.
Oh, I know. I just wanted to know if I can. So, like, for my.
You can. They don't cancel each other out. And we're going to look at a little more problems in essence. This is basically exactly where I started for, except C1 plus C2 is 2. Because remember, I just don't have my initial condition to find that value of 2. When you take the integral to c, because it's a family of functions, it can be any of those values. So separable equations basically undoes that implicit differentiation that we did back in Calc 1. All right, so let's look at a few different problems. All right, so we have our dy dx is x squared over y squared. Very similar to the problem I just did. We're going to cross multiply in essence. So we get y squared dy equals x squared dx. Your goal when you do separable equations is you need to be able to get to that. That's what it means by being separable. I can have all the y's on one side, all the x's on the other side.
Will they always be set? Like
They will not always be set like, no, sometimes you'll have to actually do some manipulation to get them separated. We'll do it. I just wanted to start off with a couple of easy ones so you can get the process down. All right, so now we've got it set up like this. I do my integral of both sides. So it's the integral of y squared. Equals, what's the integral of x squared? Only put your plus c on one side. Because remember, c can be any constant. So if I had c1 over here and c2 over here, I would subtract the c1 from the other side. I'd still have y to the third over 3 equals x to the third over 3 plus the c1 minus 2 minus c1, which is still just a constant. So I can use any letter I want. Okay, that's why we can just put the c. We don't necessarily have to put all that extra stuff there. We can literally just look at it and just the one side with the c. Okay? Does that make sense so far? Okay. Some equations, like this one, I can solve for y. And the previous one that I did, I could have actually solved for y. I didn't because I wanted it to look like the one I had at the beginning. But sometimes we can solve for y. If you can solve for y, solve for y. Get the y by itself. If you can't, you can leave it like that. So let's solve this one for y. So what do I got to do first? I'm going to get the y by itself. So what do I do? Multiply by 3. So y to the third equals x to the third plus 3c. Now what do I do? Cubed root. So y equals the cubed root of x to the third plus c. or K or whatever relative you want to use. Remember, 3 times C is still just C because C can be anything. Okay? So that's my equation. So this is the derivative that gave me at the beginning. So the beginning piece was my rate of change. The piece that I have now is my initial positions. Okay? So if we look at this, so that's my initial, that was my derivative. So if my derivative equals 1, it's that. It can be any value I want. I'm just leaving it as 1. The blue, that's my position. So the red would be the derivative of the blue, of how fast things are changing. So, and because we don't know, and we do, as of now, we don't know what the constant is, it's the entire family of those values. Every one of those equations could possibly be true. Because I don't know what C is in this situation. The second part of this problem gives you C. So this goes to y equals cube root of 3x to the third plus C. And I got to remember they actually allow you to erase on this screen. That equals 2. Yeah, it's before I couldn't do that. Like you could actually put something in and erase it, which has its benefits and drawbacks. This was one of the drawbacks. All right, so y equals 0 or y of 0 equals 2. So what is my x value? Yes, that's x, and that would be y. So I can plug these in to find C. So 2 equals the cubed root of C. So that means C equals what? 8. So no, because remember, a constant is a constant, right? So hold on, I'll go back. If C can be anything, if I multiply by 3, it still can be anything, right? So that's why I didn't need to have that 3. Okay. If it confuses you, just change the letter. Make it K. Right? That's what typically the book does. So if it confuses, yeah, just change the letter. So with that initial condition, I now have my exact answer, and that's my exact answer. Okay. Does that make sense? Kinda?
Why are we solving for y there?
Why are we solving for y?
Yeah. What's the point of it?
Because then it's in terms of a function. So if that's 8 and There. I'm like, I need it to be the exact thing there. So if my initial condition was 0, 2, which would be that would be the derivative of that function there, because that's the cube root of x to the cube plus 8. So we can now find my equation of that. Okay. All right. Let's look at this one.
Is that like why?
Oh, it's a period. Now, here's
That's what.
one of the great benefits of it. I can erase that. All right, so what's the first step? Separate it up. So I have 2i plus cosine y dy equals 6x squared dx. The integral, why we do the integral is because the integral is basically that cancels out the derivative. That's what that's doing. All right, so what's the integral of 2y plus cosine y?
Y squared plus sine y.
So y squared plus, not plus, wait, yes, plus. Sorry,
It was plus or minus.
I know, and literally taught this yesterday to my Calc 1 class. And I'm like,
Discord notification. Why? I know that's happened too, but
I don't even think I had Discord open. All right. All right, what's the integral of 6x squared? So 2x cubed plus c. I will always put my plus c on the x side. No. Like I said, you can put them on both sides, but if you're going to put them on both sides, you have to label it as C1 and C2 because they're technically not the same one. And if you put plus C on one side and plus C on the other side, some people have a very quick confidence of being able to eliminate the C's because I have plus. It's just subtractive both sides, it disappears. And it's like you can't just get rid of your C. So that's why.
If there was a reason, like in higher math, why you
No,
choose the X
no,
or
it's
the
just-
Y.
It's just a personal preference. All right. So can I solve this for y? Can I get y by itself? No. There's no way to get the y by itself in this case. So that would be my equation. I would leave it just like that. There's no initial condition in this case, so I cannot find my c.
hell yeah.
So I'm
You like that.
So if they had given you like Y of something equals something.
then I'd have to find the c. Yeah,
Yeah,
I plug the
because
numbers
y
in to
equals
find the
2.
c. Find that initial condition.
Actually, y equals 2 wouldn't work because sine of 2 is
Right.
not a real number.
No, you can find sine of 2. Sine can't equal 2, but I can find
yeah,
sine of 2.
Sorry, that it can't equal 2. I was like,
Yeah,
wait,
so it was the arc sine that wouldn't be, it would work. But in this case, it was.
why?
All right, let's look at this one.
That just means dy dx equals.
All right, yes. First thing. Very good. That's actually very important and why I did this problem. Well, one of the two reasons I did this problem. Remember, y prime is the same as dy dx.
Or in this case, would it be dx dy?
No, dy dx.
Okay.
If it was x prime, it'd be dx dy.
Okay.
So that's what I still have. So we have our dy dx equals x squared y. How am I going to separate this one? The last couple of problems, actually, all the problems we've done so far, it's basically cross multiply and be done. So this case, the y is up top, right? So I have to divide to get rid of it. So we can do this in one. We can do this in a couple steps.
dy over y.
Let's get rid of let's move my dx over. So dy equals x squared y dx. And then we can divide by the y. So I have 1 over y dy equals x squared dx.
I can do that.
All right, find me my integral of both sides.
Okay. Is that just ln y?
Mm-hmm.
All right.
So I get ln of y equals 1/3 x to the third plus c. Right?
Is
Okay.
it wrong to leave it as to the-
No. No, it's the same thing.
Isn't it just first one preference?
No difference.
it's both wrong? Zero.
You know, the day when I had my letters different from his for those systems of equations,
Yeah,
I
totally screwed
was
up.
sitting there, I'm like,
As long as the final answer comes out to be the same, you're fine. All right. Can I solve this for y? So the only time, and I can't even say you're never going to be able. If you have multiple y's, it becomes quite difficult to solve for y. Okay. So like in the last problem we had y squared and sine of y. There's no easy way to get rid of and put those together to be one y. I only have one y in this problem. If you only have one y, odds are you can solve for y. Okay. So you would want to solve for y. It's always better to get your thing back into a function.
multiply everything
Okay.
by c and by 3.
So no. How do I get rid of ln? E. Yes. So we're gonna so now everything I'm about to do now is just a bunch of algebra. Okay, we're gonna take everything and put it in the exponent of e
And it's the same now.
because I can, as long as you do the same thing to both sides, you don't change the problem.
We have to do e to the c.
Well, this is one whole thing.
Okay.
So I now have y equals e to the 1/3 x to the third plus c.
Because it cancels out the ln.
Yes.
Sorry, I sucked at this part and call it whichever part of algebra this was.
All right. Oh, I did forget one other thing. That's still absolute value. I didn't get rid of the absolute value.
Literally.
Didn't get rid of the absolute value. All right, so we've got to do a couple things now because I want my C. I need my constant somewhere so it's an easy thing for me to be able to plug something in and find. First thing though is to get rid of the absolute value, I have to do the plus or minus. So y equals plus or minus whatever's over here. That's how you can get rid of the absolute value. What exponent rule helps me with takes care of addition? Yes. So when I'm multiplying site-like basis, I add the exponents. So this is e to the c times e to the 1/3 x to the third.
This looks like straight gibberish up there to me. What we've been doing past 2-3 minutes.
That whole thing right there is just a constant. I'm not going to use c. We're going to say that's a. So y equals a, e to the, I'm actually going to write this as x third over 3, just make it a little cleaner. And that's my final answer.
Mr. Baker,
Yes.
on the website, could you put a link, one of your videos about this specific stuff with E and logs and.
Send me an
algorithms?
email to remind me because I'm never going to remember tomorrow
Thank
to do
you.
it. But send me an email.
I constructed this.
I
This is the reason I failed the test. This.
I probably have something for my pre-calc class on exponents.
You're right, we would say, but then I would say.
Oh yeah,
I
but
don't think there's anything in the pre-calculus.
yeah, there's a whole bunch of videos in it.
There
I
was
still
one
want
that
to know
was
how to do
empty.
this. Understand, we'll be doing higher
I
math.
can't
So it's
remember
like,
what it was.
Maybe college algebra
I also took it with Kennedy.
because it took me forever. Well, it was so long ago before since I did that.
Oh, God, like, it's like that one, I was like,
That was probably the one I would have looked at. Screw.
Oh no, they both have stuff in them. Calculus 2 did, or Calc 1 didn't have anything in it at the beginning of the semester
Maybe that's what it was.
because I just started that one because this is the first time I've taught Calc 1 and Calc 2 at the same time. Normally I don't, so I just use Calculus, just put the notes in there for the class, and it's not that big of a deal. But since I'm teaching them both, I could have them mixed because it would have totally confused everybody. So, all right. So yeah, that's, again, there's a bunch of algebra to go down. But yes, send me an email. I can, if I don't have one, I'll find something that will go over that stuff for you. No problem. All right.
it just equals 2.
Let's look at this.
I don't like that.
I know. So the reason I did the last one and the reason I did this one is as compared to the first ones were set up very simply to get you to understand what you can do. You can set it up any way you want. Like you can have them in a bunch of different ways. Like this one, the y, it isn't even equal to y prime.
Yeah.
Okay, so the y prime is actually part of the actual problem, but it doesn't matter. And that's the thing that unfortunately you have to get past. It's like, even if it's all jumbled up, the process that you're doing stays the same. Okay.
That's just still be like the X.
Right. So we changed that. So I have x
Oh.
ln of x equals y, 1 plus the square root of 3 plus y squared dy dx. And now all I have to do is move that over there.
And that's exactly what the other way around.
Okay. Find me my integral both sides.
The left side? It's integration by parts, but I'm pretty sure we did that at one point.
It is integration by parts. And we probably did do that one at one point. XL and X sounds familiar. I probably did those at some point. But if you don't have it, find me the derivative. Find me the integral of it. It's good practice to remember how to do integration by parts.
That's just L and X.
Oh,
The U,
Oh,
the
it's a
U,
triple
V, the V.
integration. That's a triple
No,
integration.
No, it's not.
We have L and X in our notes.
Oh, we don't have XL and X.
we didn't.
Yeah.
Oh, so just do integration by parts.
Because I don't want to do. I don't want to do this.
It only has to be done once.
True. And then the other side is what we've done recently, right?
The other side should also be, actually, the other side you should be able to do simply. The other side does not need any real
Use sub?
special rules. You do use substitution, and that would be it.
U equals Y.
No, U does not equal Y.
U equals 1 plus.
No.
3 plus Y squared.
U is going to equal 3 plus Y squared, but you need to do something before you do your substitution.
I need to cry. We could symbol that.
I'm not for it. Because I'm too lazy to make that. I'm gonna look for it. Gotta find it. Okay, so I put it through all my areas. You're going to find it.
Oh, yeah, that's
Thank you.
Because otherwise it looks like you're still doing the LN of that, and that'll be.
Fine.
Holy shit.
Did you find it?
No, I was just really stupid while doing this. Holy moly.
All right, let's do make that blue. I have a ton more colors now. That's a plus. Make that purple.
Ooh, much of it.
Yeah, that's what I said. I have a ton more colors now.
Oh, actually, should be blue.
It just. I got it.
Why'd you put a 1/3 out?
Because technically it's 2/3, but you have to divide by the 1/2 from the derivative of 2y. I'll do that in a second. Let me finish this one.
Y squared over 4.
For which one?
Or
This? Where? Oh, which side? The Y side? Where did you take out or how did you take it? Where did you take out the 1/2 from? Oh, you didn't. So when you're doing this side, there's two pieces. That's the only one you have to do the du to the u to. So the 1/2 doesn't impact this part at all.
oh, it's like the U to U.
Right. So u is 3 plus y squared. So du is 2y. So 1/2 du is y dy. But you're not looking at that part at all. That's done. That's actually where the 1/3 comes from, because I have 1/2 times 2/3, 3 plus y squared, or y squared, to
Oh,
the 3/2. And that cancels out. That's where the 1/3 comes from. So your final answer is x squared over 2 ln of x minus 1/4. Oh, I forgot the plus c. Plus c.
Yeah, you threw me off because when you had them like that, but then so I was like, you didn't write down any use of.
Yeah, because I did it as an implied u substitution at that point.
That's why I got confused.
Yeah. Which I shouldn't have, because it was a y squared and not just a y. But it in essence was up to be the same.
I did right.
It's v.
That's what I was actually whether what I'm doing it correctly.
Yeah, so it's uv minus the integral of v du. So outside is u and v. That's where the x squared over 2 ln of x comes from. Minus x over 2, 2. So times 1 over x dx. So the 1x cancels out. The 1/2 stays from that. And you have x squared over x, which is just x. No, that's fine. So you end up getting x squared over 2 times 1 over x. So the 1/2 x squared over x is just x. That's what I can. All right. Yeah, that's not good.
Oh.
Okay. You're fine. All right. Oh, yeah, that's good stuff.
This won't happen. That's how you run.
Yes, I'm erasing because I'm going to do the other part of the problem.
Oh yeah. Why do you have to do us like that?
So we have x squared over 2 ln of x minus 1 over 4 x squared plus c equals y squared over 2 plus 1/3 3 plus y squared to the 3/2. All right, so in this problem, they gave me my initial condition, y1 equals 1. So they made your life easy. we're just going to plug in ones for everything. So that becomes 1/2. ln of 1 is 0 minus 1/4 times 1 plus c equals 1/2 plus 1/3 for,
I'm sorry, why does
Three
the
halves.
y of 1 equals 1 mean that we can plug?
because that's
I
x,
get it.
that's y.
Thank you.
Mm-hmm. So 1/2 times 0 is 0. So I have negative 1/4 plus c equals 1/2. 4 to the 3 halves is 8. So c equals 1/2 plus 8/3 plus 1/4, which is 6, 32, 3, 41 over 12.
So it's differential equation, and what we're doing is just a way for us to find our c in our original equation.
No, differential equations is the ability to find the initial conditions of any situation. So in differential equations, you're given an equation that is a rate. You're given a derivative, or your second derivative, or third derivative, whatever it happens to be. You're given that, and you have to go backwards to find it. So you basically have to do integration. Problem is not every one of them is going to be set up as a function, which is what every problem we've done in chapter 7 was a function. Every problem we did in chapter 8 was a function. It was f of x equals, m of x equals, whatever happens to be, they were all functions. This expands you past a function, so you can do things that are not functions.
That's a function, right?
The original problem, or this, is not. It'll fail the vertical line test.
Oh. Yeah.
That's the difference. So because it fails the vertical line test, it is not a function. In the situation where we had a couple of them that were, like this one right here is not a function at the end. This one, we were able to solve for an actual equation. The actual equation at the end was a function. It would pass the vertical line test because I could solve for y. When we did this one, we were able to solve for y at the end. So I do have a function here. So, okay. All right. So let's do this one. Because as crazy as this one looks, it's not nearly as difficult as it looks. So in electrical circuits, finding the rate of change in your circuit is actually extremely important for figuring things out, especially in digital circuits. So finding out how fast things change, how fast the current changes, how fast the resistance possibly changes, and stuff like that is needed. And those are all derivatives. So in this situation, they want us to find what's the limiting value of the current. So they want us to find out what's the highest current you could possibly get. Does it actually converge to an actual value? It's basically what they're looking for. They're giving you your equation. That is your differential equation. They're giving you information to plug into that equation. So we have our initial equation there. For those of you who do not know anything about electricity and electrical circuits, the L stands for induction. So the L in this case is 4. So L equals 4. R, resistance. So R is 12. And E of T is your voltage, which in this case is 60.
The DI.
Yeah. Because we're looking for I. I is current. I is your amperage.
I hate that they make I and L the same.
and we're looking at its change over time. That's where the dt comes from. Okay, so let's plug our information into the problem and see what we got. So I've got 4 di over dt plus 12I equals 60. All right, so the goal, let's see if we need to get the i's on one side and the t's, which I don't have any, on the other side. But the real key is to get the i's on one side so I can have that di, so I can do my integration. So let's go through and solve some stuff. Ben, right?
Yes.
I didn't call him Shrek.
You actually caught me off guard. I was like,
He actually remembers my name. He said we can divide everything by 4. So we can divide everything by 4 in this case, which will help me get rid of that 4 there. So I have di over dt plus 3i equals 15.
now we can do 15 dt equals 3i plus di.
So let's move the 3i over the other side. So this way we can get the di over dt by itself. Okay. How do we get the I with the I and the dt by its with the t's?
Isn't there some fraction rule?
Why didn't you just multiply, before you did that step, why didn't you just multiply both sides by 8? Or 9?
Because I would have had also multiply the 3i by dt. But believe it or not, that actually wouldn't have been a horrible step. If I did that, I would have had this. 3i dt equals 15 dt.
Yeah.
Then move the 3i over like I did here, right? I'd have di equals 15 minus 3i, and I could factor out the dt. So both of those would have worked because they both have dt in it, so I can pull the dt out. So your step would have, the only downside to your step would be you probably would have forgotten to multiply the 3i by the dt.
Oh,
So, but it would
you
work.
started writing it down, you were writing something different, so I was like.
All right, but I don't have the i's with the i's and the t's with the t's.
Yeah.
So what do I got to do?
Some algebra stuff.
Yeah. I need to get this, or at least the 3i, but the 3i is with the dt, so I can't just pull out the 3i over here. How do I do that?
Divide by.
Yeah,
Oh,
literally
okay.
just divide. Divide both sides by that. So I have 1 over 15 minus 3i di equals dt.
You had me scared. I was like,
One of the other nice things about this thing, I have infinite space on the screen.
So
All right, so now what I got to do? I do my integral of both sides.
is the integral of dt just t?
Yes.
Okay.
All right, so how do I find the derivative of, huh? Yeah. The negative 1/3 ln 15 minus 3i. You should have remembered that from partial fractions.
I knew there was like one swift step to do.
Yeah. Okay.
Actually, never mind.
This is what t is equal to.
Since we've already done it once, I don't feel like doing it again. So,
Hell yeah.
Oh, I looked at my document.
huh? Well, no, because I gotta get the I by itself. But since we had already done one like with the LNs, I just didn't feel like writing it all up the steps again. The process is exactly the same though. It's like that's so you get rid of your ln by doing the e, absolute value with the plus or minus. You can split up the e's like we did before and get the a. You move the 15 over, you divide everything by -3. That gives you 5 minus 1/3 a e to the -3t. Now, if I did the limit of this, what's e to the -3t going to go to? As it goes to infinity, what's that going to go to? That's going to go to 0. So the limiting factor of so this piece is going to go to 0. So I goes to 5.
Not the limits. Then we plug I back in.
No, that's I. We're done.
Oh, thank God.
One.
We're not done with the class.
I mean, yeah.
Done with that problem. But you can start to see how like this stuff's really, again, just like we were talking about with the stuff in chapter 8 afterwards.
Limits popping back up.
This stuff's used. Like the other stuff that you need that was there when we go to chapter 11, we're going to use a lot of limits. Limits is going to be like one of our main things with chapter 11. So no, the other stuff that you learned did not go away. Like we had to use the stuff that you do with partial fractions with this one. This one you had to use integration by parts. So it's like that stuff still is there. You still need to know that stuff. That's why we did it before we did this stuff. So. All right.
Except for the next card. Integral of UdV equals UdV.
Mixture problems.
Could we technically solve this for algebra?
I don't think so. Because it gives you a rate and you're looking for, in essence, a limit at the end. You're looking at what things go to. There are similar problems that are done with algebra. Like if you have a solution that's 30% something plus another solution that's 70% something, how much of each solution do you need to get like a solution of 50% something at the end? Those you did algebra for. And they're similar to this, but not exactly the same.
I'm sure, like, you know that there's like.
And if you could do algebra to do this, which is I guess it's possible if the longer I look at it, it's gonna be way more work than what I'm gonna show you.
Okay.
equations like this and then come to with just algebra. and then in that calculus.
Yeah,
It's
you,
possible to solve if you know the molecular weight of each.
right. That's what I'm saying. There's other stuff that you need to know. Right. So we're going to look at this in terms of differential equations because that's what we're talking about. So the salt level is going to be the Y. So that's the rate in minus the rate out. Because we have water coming in and we have water going out.
Feels so good, brother.
Okay. We have stuff coming into the tank and stuff going out of the tank. So it's a matter of how's the mixture going. Now, the water coming into the tank and the water going out of the tank is at the same flow rate. So the tank will stay the same volume over time. There will always be 5,000 liters of water in the tank. Doesn't matter in this situation.
Actually, it's exactly just hot enough that everything in there expands just a little bit.
All right, so let's look at the rate in and let's look at the rate out. Let's figure out what those pieces are. So my rate in, I have how much salt coming into the tank? Yeah, I have 0.03 kilograms per liter. And it's coming in at 25 liters per minute.
Liters cancel.
Correct. So I have 0.75 kilograms per minute.
I don't know, but can I drive that? Like, what's stopping me?
They're really cool Zabonis. All right, what's my rate out? How much salt's leaving the tank?
Same amount.
No. Because whatever the mixture is going to be at that point, right? So we don't know how much salt's leaving the tank. That's your Y of T per liter.
It just says the solution is kept.
It's still 25 liters per minute.
Oh, I see now.
So your rate out is 25 Y of T over our kilograms over a minute. Oh.
Taking the salt
Eh.
baths.
I forgot one thing. We do know how much water's in the tank.
Yeah.
So that's not, it's going to be 1 over, what's it? Over 200? Yes.
12 to 200.
There's pizza.
All right, we good to there?
Do we need the 5,000 liters on the bottom of the rate in?
Yes. Because, so the rate out, this is the amount of salt that's in the entire tank, the Y of T. I know there's 5,000 liters of water in the tank.
What's about rate in?
No, we don't need, because
Okay.
we don't know. So the liters coming in, that's how much salt it is per liter coming in.
Okay.
So, and then that's per minute.
I was like,
We're not putting 5,000 liters into the tank. There's 5,000 liters in the tank already.
which is why it's
Over 5,000, yeah. All right, so my dy dt is 0.75 minus 1 over 200 y of t.
And that's just everything simplified.
Yeah, that's my rate in minus my rate out. So we can clean this up a little bit. We can put this together so it's one equation because we're going to need to do that. It's 150 minus yt over 200. Okay. Separate it for me.
Oh, y of t is a t value.
No, that's a y value.
What is y times t?
No, it's y of t.
Yeah.
So it's a y.
Okay.
That's just y. So that goes with the dy. It's like f of x. It's not an x value. It's a
Yeah,
y.
that's why I was. Yeah.
Oh, that's nice. That's useful. Right click gives me my pen color so I don't have to click on the thing. That's useful. Because I can actually, I gotta change that. There we go. I was gonna say because my pen, the little click, that's a right click. So that's helpful. Learn the little tricks of the new program. All right. So if you cross multiplied, the y's and the t's are on the wrong side. So then you have to divide both sides by the other things. That's why they end up down the bottoms. This one just comes out to be a simple, same thing. U substitutions, it's 1 over u, ln of u, and then it's a -1, so that's where the negative sign comes out in front. 1 over 200, it's a constant, so you just add the variable. That's where the t over 200 comes from. Now, in this situation, we don't have to solve necessarily. So they gave me the values for at the very beginning. There was 20 kilograms of salt in the tank at the beginning. So I know, so that right there says y of 0 is 20. So I can use that to figure out my C. So that's 0, and that's, no, sorry, wrong way. That's 20, and that's 0. So I have negative ln of 130 equals C.
Do we want to just find the natural one the 130?
No.
Okay.
The question wants to know, the original question, is how much salt is in the water after 30 minutes or a half hour? So we need to take and plug in 30 for T.
What about the Y we've got there?
Huh?
What about the Y we got?
We have to solve it. We have to solve for Y.
Oh. Yeah.
So T equals 30. So now we got to solve. Thirty over 200 minus ln of 130.
At least one.
At this point, I would do the 30 minus the 30 over 200 minus ln of 130 and get that as a number.
Okay.
So, which plugging that into Desmos gets me negative 4.718.
Does that work out nicely to a fraction or no?
No.
And then we take our
Yes, now I've got to do, well, I got a negative sign first. I got to get rid of that. Right, because there's negatives on both sides, so I can get rid of my negative sides. Now I've got to do the E of both sides. So I've got 150 minus Y equals E to the 4.718. Sorry, plus or minus.
so we have
Subtract the 150. And now get rid of my negative side. So we've got E to the 4.718 minus 150. Somehow my sign got messed up, and I don't know why. Oh wait, that's why. Plus 150. So we get Y can equal 261.9 or Y can equal 38.0 or 0.1.
the
Yeah. So this one doesn't work because if we plugged it in on this side over here at the beginning, it would have given that side as a negative value. So that doesn't work. So The answer is 38.1 kilograms of salt in the tank after 30 minutes. So we started off with 25 kilograms of salt in the tank, or 20 kilograms of salt in the tank, and now we're up to 38 kilograms of salt in the tank.
It's not per liter.
It's total, right? It's how many kilograms at that point. That's what we're trying to find. We're trying to figure out how many kilograms is in it. So that's really the difference in this. That's why the original problem was a derivative or a differential equation, because it was a rate. It was kilograms per minute. So we have the rate of change at that point. So that's how we know it's a derivative. Where at the end, I've taken the integral of it, so now it's no longer a rate anymore. It's the actual total amount in that tank. So we've now found the actual amount of salt in the tank, not per minute. It's the actual number of salts in the tank. So it's 31.8 kilograms of salt over in a 5,000 liter tank. So I've told you I'm writing a math textbook, right? And so the math textbook typically will be used for high school students that are doing this stuff. So we're not going to do this problem, but we were writing a differential equation section in the book, and I had this problem because I'm like, it's a good problem. And she goes,
The children are only.
children should not be drinking alcohol. Oh yeah, that's right. So, but it's the exact same thing as we just did with the problem. It's the same concept. So this is what your
I'm sure like some parent would like write you.
oh yeah, it's absolutely
Horrible.
This is what I come back to.
absolutely. We're not doing it. But your brewmasters have to do this to be able to sit there and change the alcohol level in.
See, that's why we have a family brew. We don't care. We don't care.
So, all right. Enjoy your spring break.
Oh, that's it? That's it.